Good morning, everybody, and thanks for joining. I know replay was last night, and I'm actually extremely impressed with all of you for making it to a session this early in the morning, the day after replay. It's been a really exciting week, lots of great announcements, and today I'm here to talk about AWS Outposts. AWS Outposts brings true full AWS anywhere you need it to be, and this is something that Andy announced as a generally available product on Tuesday. Really excited to talk more about it. My name's Anthony Liguori. I'm a senior principal engineer in EC2. I'm the engineering lead for Outposts. Prior to that, I led the Nitro project. So the thing I get the most excited about, the thing that really drives me, is the interaction between hardware and low-level system software. So I do hypervisors, kernels, all the really low-level stuff. And one of the things that's most exciting to me about the Outposts product is that not only can we deliver all of the interesting and exciting value to customers with this product, but now it's hardware that powers AWS that you can actually see and touch and really understand how it works. I had a co-speaker for the last two versions of this session. He unfortunately had to head back to his location, but there is a video on the website, about 5 minutes or so, where he talks roughly about what the use cases are that Philips is using Outpost for. So I'd encourage everybody to go to the Outpost product page, and you can see that video and hear how Philips is using it. In this session, we're going to talk about what AWS Outposts is. We're going to go deep on how it works. There are a number of new things we had to introduce as part of the Outpost project, among those ordering and the installation. Today, the way you launch an EC2 instance is you just run an API call, super easy. Obviously, for getting a rack of capacity in your data center, there's a lot more logistics involved, and we'll talk about those logistics. But we've tried to make that experience as easy and as painless as possible, and we'll walk through what's involved. Finally, I'm going to talk about how AWS services interact with Outposts and how we're thinking about that interaction, and kind of give you a sense of how we're thinking about services on Outposts over the long term. What's really exciting about Outposts is we really are at day one. It's really early, and I think you're going to see lots of exciting things happen over the next few years. And then at the end, I'll make sure to leave time for questions that anybody in the audience might have. Now, as I mentioned at the start of the talk, fundamentally, I'm an engineer. I love hardware. I love software. There's no way I'm going to get up on stage and talk about Outposts without first showing pictures of hardware. And so that's how we're going to start this talk, because this is what excites me. And hopefully, if you're in this talk, this is what excites you too. So this is what an Outpost looks like. I'm just out of curiosity, how many people in here are familiar with data centers and racks and have seen racks before? Perfect. OK. So it looks a lot like a standard rack. In fact, it fits in a standard rack position. The insides are very different, though. And hopefully, you can even see from this picture that some of the things are pretty different. The first thing I'll point out is that this is the hardware we use in our data centers. And in our data centers, something that's really important to us is that we try to eliminate unnecessary cost wherever we can. A lot of racks, especially in the sort of hyper-converged space, they put all this industrial design, this fancy plastic and stuff like that. None of that makes it go faster. None of it makes it more efficient. We tend to have a more Spartan design because ultimately we're trying to deliver the best value and cost. This is the inside of the rack. At the very top, we have a patch panel. This is where you would connect the uplinks from your local network into the rack. From a networking perspective, we expect 2 uplinks to be connected into your network. Those uplinks can be 1 gigabit, 10 gigabit, 40 gigabit, or 100 gigabit. We like to use BGP to interface with your network. If your network doesn't support BGP, we can do static routing. It's just more complicated to set up and maintain over time. So we really recommend that the networking drops that you bring in do support BGP. Within the networking drops, we expect to see 2 VLANs. One VLAN needs to have connectivity back to the AWS region, and I'll talk a little bit more about that later in the talk. And then the second VLAN connects to your local network and is how you can interact with your low latency applications locally. In the middle of the rack, we've got servers. We typically have one-use servers. A power shelf, which is how we do AC to DC conversion, and 3 switches, 1 for management and then 2 data switches, which actually connect to your network. And then finally, we have some more servers. You'll notice a lot of empty space in this rack. This is a 15 kVA configuration. We have Outpost configurations available today that come in 5 kVA, 10 kVA, and 15 kVA. We actually can go much higher than that from a power perspective. We just find that most data centers don't support more than 15 kVA. We design our racks for 25 kVA, which is why there's so much empty space in the rack. But most data centers don't have that. If you watched Peter DeSantis' keynote on Monday night, he actually showed a picture of a C5N server opened up compared to a C5. And he showed 1 Nitro card in the C5 and then 2 Nitro cards in the C5N. This is exactly that same hardware design. And so if you can see, there's 2 network cards towards the right-hand side of the server. Those are actually 2 Nitro cards. So when you get an AWS Outpost, you're actually getting the same Nitro hardware that we use in our data centers into your local data center. The other thing I'll mention is that when we deliver racks, this is exactly how they come. Everything's pre-cabled. The cabling is all bundled neatly to the side. If you've dealt with data centers a lot, particularly if you have your folks build racks by hand, often they don't look like this. They can be a little bit of a spider's nest of cabling, but we're very, very specific about how we cable the racks. It's very important for us for maintainability of the rack. Within the middle of the rack, we have our power shelf. So this is one of the ways that our hardware differs pretty significantly from a lot of what you'll see in the industry. There's been a lot of talk this year at reInvent about energy efficiency. And at our scale, energy efficiency is great for the environment, but it's also great for improving costs. Typical servers will do AC to DC conversion because all of the components in a server generally are DC powered. There's not really a need for AC, but the typical thing is that every server has its own AC to DC conversion. And doing that in a small form factor is way less efficient than doing it in a large form factor. The second problem is that power supplies are actually one of the components in hardware that tends to fail the most. Usually it's hard drives, DRAM, and then power supplies in terms of what fails most commonly. And so then you'll see that a lot of servers have 2 power supplies. With our racks, we do N+1 redundancy for power supplies. That helps improve cost because we're not doing a whole bunch of duplicate power supplies, but it also improves reliability because now you actually have way more redundancy than you could have if you did it in every single server. And the back of the rack, you can see that this is the actual bus bar. So it's 2 large metal bars that all of the servers plug into. One of the consequences of this is that our servers are always full depth. This is very unusual in the industry. Usually, servers are about 36 inches long. Ours are the full 48 inches long. So they go all the way to the back. One of the benefits of that is that we can actually fill the servers completely. So we can put more disks, more RAM, more processors in a single one-use server. It's one of the ways that we actually achieve density. The second way that we achieve density, if you're really astute, you might observe that the servers are wider than is traditional in a rack. Typically, you've got 3 or 4 inches on either side where there's rails. We extend the rack, or we extend our servers to be 21 inches wide to get as much of that space as we possibly can. And again, this just shows you the iterative design that we've had over the years of trying to get every little bit of performance and capacity out of our data center positions. Okay, so I've satisfied my need to geek out a little bit about hardware. We'll go back to kind of the normal presentation. So AWS Outposts fundamentally brings AWS on-premise. The way we do this is by using the same hardware as we've talked about. But another key important point is that we're using the exact same software on that hardware that we use in the region. So there's been many, many announcements this week. In fact, not just this week, but last week there were many, many announcements. And when you see an EC2 or a VPC feature announced, as an example, multicast, Because we're using the same software in the Outpost, when we announce it in a public region, it's there in Outpost 2. An Outpost is fully managed and monitored by AWS. What that means is that we are actively monitoring every piece of hardware in that rack to identify when there might be failures. If there is a failure, we'll actually contact you to schedule a replacement. And if anything is behaving in a strange way, we'll investigate it. So the goal of AWS Outposts is to give you the same experience as operating capacity in an AWS region. We don't want you to have to be hardware experts or debugging server experts. We want to continue to bring that service as part of AWS Outposts. And then finally, because of all of this sameness, you actually use the exact same management tools in Outposts that you use in a public region. This includes the AWS console. In fact, it's not even a separate console endpoint. If you create an Outpost that's associated with the Oregon region, then you use the Oregon console to manage the Outpost. Likewise, the SDKs, the command line tools, it's all the same. One of the important consequences of this is that third-party tools that also have been built to manage AWS capacity largely can be used to manage an Outpost without modification. So we've showed a lot of pretty pictures of servers. We've talked about sameness. But one of the questions we always get is, OK, well, why now? Why are you just doing this now? Why didn't you do this a long time ago? In fact, there's kind of a joke that we like to tell internally that EC2 has been around for about 13 years. And there's been a proposal as part of our annual planning process to do EC2 on-prem literally for the last 12 years. It's been a problem that we've been trying to solve since the very beginning. And until recently, we never really came up with a solution that we felt was going to be the right type of solution for customers. And when we don't think we can build the right thing, we're not just going to build it anyway and put it out in the market. We'll hold ourselves to the right standard. So I wanted to talk a little bit about why this is a difficult problem, why it took us so long, and ultimately use that to show you how Outposts works and why it's so different. And to do that, we really need to start with what happens when you create an instance within EC2. And so if I were to run the AWS EC2 run instances API via the CLI, from a user's perspective, I launch the command, and about 20 seconds later, an instance appears, and I can SSH into it. Seems like a relatively simple thing. Behind the scenes, there is a lot going on. In fact, as much as I like to think that the hypervisor and the hardware is the most important thing in the cloud, the reality is there's probably 100 times more infrastructure involved in launching an instance than the hardware and software that I work on personally. The very first thing that happens when you execute an instance is that you talk to an API front-end service. We love microservices. All of our systems are built as a series of microservices. And we find that this allows us to iterate features very, very quickly. But it also allows us to scale teams horizontally so that we generally have a 2 beats a box team working on each of these microservices. And it's allowed us to grow at the rate that we've grown over the last few years. From a hardware perspective and from an instance perspective, all of our microservices are designed to be 3AZ. And this is the pattern that we recommend everybody use. But what this means is that if any individual availability zone has a problem, the other 2 availability zones can take over and handle the workload. And so this is really important for API availability. And we design all of our services to act like this as long as it's appropriate. Now, the other thing that people don't always think about is that if you do have 3 availability zones, you can't just have 1 machine in each of the availability zones, because hardware fails. And you also won't be able to absorb the difference between peak and idle workloads. And so you'll either need a really big machine, or it just doesn't really work very well. So what we typically do is we have at least 3 machines, no matter how much load the system has. And we have those three instances have to be physically diverse. We don't want all of them to be on the same physical machine, because if so, then that single physical machine would take out all 3 instances, and you would lose the entire availability zone. After we talk to the front-end API service, that service, after it's validated, authorization, authentication, it usually redirects to another control plane service. So in the case of an EC2 run instances, we have a front-end service that handles creating an ABS volume, handles creating a VPC ENI attachment, and actually a front-end service that handles the instance itself. Again, these services require at least 9 hosts in order to function properly. The other thing to mention here is that in addition to having the hardware and software for these microservices, the thing that fundamentally makes a service different from a software product, like a shrink-wrap software product, is that services are operated by people. Each of these services has a dashboard, and there's humans that are monitoring the dashboard to look for anomalies and try to figure out if things are going oddly. There's alarms, and there's people that will receive pages if something goes wrong in the given service. I think that is really the thing that is different about cloud versus what we've been used to for the last 20 years, is that cloud also comes with ops. And ops is really important to keep a service healthy and happy. After a front-end service gets involved, usually the next step is a database backend, and that can be Dynamo for services that can use Dynamo, or it can be something very custom in the case that this is one of the real primitives of AWS. But the key observation here is it's not just these 3 services. There's actually hundreds of services involved in a EC2 run instances API call. And when you start multiplying the combination of those hundreds of services with the number of instances required, you end up with thousands of individual machines that are all involved in doing that single run instances API request. Now that sounds like a lot of capacity, but our regions are very, very large. And so those thousands of virtual machines actually are just a drop in the bucket. This is where economies of scale in a cloud and in AWS really work to your advantage, is that because everybody's sharing that control plane, everybody can afford to have a very, very robust and feature-rich control plane. And this is where the problem lies. The problem is, how do you fit this into a single rack? How do you fit thousands of machines, virtual machines, into a single rack in a way that can emulate that behavior? The answer to date, and the thing that we had always talked about, because that's what the rest of the industry has done, is making compromises. One of the compromises that you make is you say, I'm not going to try to have high availability. I'm going to shrink those 9 VMs per service into a single virtual machine. And if the hardware fails, you're just going to have an outage. You're going to have an availability event. So you end up with poor availability. The second thing that you inevitably do is that microservices work great in a large-scale system, but if you're really, really capacity constrained, as you would be in a single rack, you're going to be very tempted to combine those microservices into a monolithic service so that you can deploy more efficiently and also have more efficient use of capacity. The problem with a monolithic replacement of microservices is that no matter how rigorous you are in trying to be API compatible with the original control plane, there's going to be an uncanny valley. The most typical place this occurs is with error return codes. If you're writing automation or you're building a system on top of a set of APIs, often the error codes are not as well defined as you'd like them to be, but you do have to take behavior based on why things failed. You're going to do something differently if there's an authorization failure versus there's no resources available and you have to retry later. And these differences are really important. A great example of this is actually the POSIX APIs, the thing that Unixes are based on. If you've ever written an application for AIX and HPUX and Linux and had to support it across all of those different environments, even though POSIX is a very, very well-defined API with huge committees behind it that specify every little detail, over the years, those implementations don't behave the same. And you just simply can't write code that works perfectly across all platforms. You end up having to test on every single platform and develop special handling for specific platforms. This is fundamentally something we don't want customers to have to deal with. We don't want customers to have to special case their code for on-premise capacity, because that ultimately defeats the purpose of having AWS on-premise. The second issue is that fundamentally you're dealing with a different software stack. Because you've likely rewritten your software into a monolithic service and gotten rid of the multi-AZ availability, you probably have a very, very different code base. And in fact, all of the things that are out there today, with the exception of Outposts, are based on different code bases. What that means is that even unless you're making double the investment and you make a really strong commitment to not have any differences in features, you will end up with feature gaps. And most likely, the on-premise version of your control plane is going to lag behind in features, which means that when you have an event like this where someone gets on stage and announces hundreds or even thousands of new features over the last couple weeks, a lot of those just won't be there. In fact, most of them probably won't be there, and who knows how long it'll take for those features to get there. I fundamentally believe, I truly believe, that you cannot build the cloud in one rack. It's just not possible. It's not the cloud. It's more like the system management software that we've been dealing with for the last 20 or 30 years that everybody has lots of experience with. It's just rebranded. You've just taken those typical system management tools and rebranding them to something that it's not. Now, all that said, I'm here talking about Outposts, and we had an Outpost rack in the Expo Center. Hopefully everybody got to see it. So we think we've solved this problem. Let's talk a little bit about how we could solve this problem. The way I usually like to tackle things like this, where it seems like there's no way we could solve the underlying problems, is to start with a simple solution that might have flaws and then figure out how to work around those flaws. So there's actually a very simple solution here. And the simple solution is we could take the customer's data center and we could just connect the network of the customer's data center to our network in a region, and then we could just use the control plane in the region. And that would work, right? There's really no reason why it wouldn't, as long as we are landing our hardware in the customer's data center. In fact, James Hamilton has talked in the past about how our availability zones actually consist of many data centers already. So we have all of the infrastructure we need to connect additional data centers into our regions and availability zones. So this would work. And the reason this works is that we're basically turning whatever your corporate data center is into an extension of our region, and specifically an extension of one of the availability zones. Fortunately, it's not this simple. Things never are simple like this. The first problem we run into is that we violate trust boundaries. As much as it's important to have security in software and hardware, physical security is still important. If you have physical possession of a piece of hardware, even if you have the most sophisticated anti-tamper mechanisms, you're likely going to be able to get at the data in the hardware. One of the things I like to use as a test when I'm talking to people about security is if they use the word tamper-proof, I know that they don't know what they're talking about, because nothing is tamper-proof. Give it enough time and energy and enough money, you can always tamper with a physical piece of hardware. So the word I'll always use is tamper-resistant, and really that's the best you can be, is tamper-resistant. So there's a fundamental problem that if we don't control the physical security of a piece of hardware, then we can't trust that piece of hardware. That's not necessarily a bad thing, because if you have hardware in your data center, you trust that hardware, and as long as you trust that hardware, that's fine, right? Because it's your data, it's under your control, and you're the one that really matters in terms of whether you trust that or not. The problem, though, is that there's actually this really great paper called Trusting Trust, and it talks about how you bootstrap trust using compilers as an example. So if you compile a piece of code, and you can be really sure that the code is correct, but how do you know there's not a backdoor in the compiler? Well, you could look at the source code of the compiler and try to figure out if there was a backdoor. But the compiler was compiled with a compiler. And you end up with this infinite loop of, okay, well, how do I get to the very original binary that was used to create the, and ultimately, like, you just have to trust something. You have to pick a turtle, effectively. So the way that this problem is often solved in terms of trusting a large-scale infrastructure is by doing a distribution of a shared secret. If everybody has the same shared secret or a derivative of the same shared secret, then everybody can kind of agree and trust each other. And that works well when you control physical security, but if you don't control physical security, you run into the problem of how do I store that shared secret in a way that I can trust that nobody else has that shared secret. So bootstrapping becomes a major problem in this type of architecture. To be a little bit more concrete about this, think about pushing logs. So a hypervisor or any other operating system or component, you need to get logs off of the server and stored somewhere centrally so that you can do troubleshooting and diagnostics. The most obvious way to support getting logs off of a server is just to have an agent that runs on the server that pushes logs into a remote service like CloudWatch. That doesn't work in this model because you need the credentials to push into CloudWatch, and you don't want to share that account across all of these devices. Finally, the problem that you run into is software update. A lot of cloud infrastructures have been designed to rely really heavily on live migration and basically having pools of unused capacity that you can move things to so that you can perform deep updates of the system. There's providers out there that actually retire entire data centers and upgrade the data center all at once in place. This doesn't work when you have a single rack. In that single rack, you're going to be very capacity constrained, and typically, customers are going to use as much of that capacity as possible. So reserving entire servers of every type just isn't really practical. It turns out, though, that we've been working on a new platform for the last 7 years now called Nitro. And Nitro is really a ground-up rethink of how the hardware of a hypervisor and the software works. And because we've been thinking about this problem for so long, when we've designed Nitro, we designed it from day one to help solve this problem. And even though some problems seem intractable when you're trying to retrofit it into an existing system, when you're starting clean room, when you're starting from a new implementation, as long as you're keeping the right things in mind, they actually become quite tractable and solvable. So ultimately, Nitro consists of 3 things. The Nitro cards, which are based on silicon that we build, related to the Graviton2 processor that was announced here at reInvent. The Nitro cards handle all of the I/O virtualization on the platform, so your networking, your storage, both EBS and instance storage. They also act as the controller for the overall system. The Nitro security chip is the thing that manages the security of the overall system. And the most important thing it does is it establishes what's called a root of trust. And I've done presentations in the past about how this works, if you're interested in it. But effectively, the Nitro security chip is the thing that establishes an identity that we can use to bootstrap the system, and it really addresses this trusting trust problem for us. And then finally, the Nitro hypervisor, which because of all of the other things we've built, is actually very lightweight, and it also has the capability of doing what we call live update, which Werner talked about in his keynote on Thursday. Live update actually allows us to do in-place software updates of every component in the system while your instances are still running without your application experiencing any downtime. What this means is that we can actually do a full update of a single rack of capacity without having to have buffer capacity sitting around because we're able to do this live update capability. So given this new capability of Nitro, let's look at how we actually implement Outposts under the covers. The really cool thing about Outposts is that it's actually quite simple. There's really 2 things that we had to build to make Outposts work. We also put a logo on our racks. Our racks typically don't have logos. Believe it or not, that logo took about 12 months because physical machining is hard, apparently. From a software world, you don't think about that, but actually physically building things takes a long time. But from a software perspective, we had to introduce 2 things. One is the Outpost edge device, and the other is what we call Outpost proxies. So between the Outpost proxies and the Outpost edge device, we establish a VPN connection over what we call the service link. So this is one of the two networks that we expect to come from the uplinks to the rack. And the service link can be carried over the internet. We can establish a VPN tunnel over the internet. Or the service link can be carried over a direct connect private VIF. So if you have direct connect, you can leverage direct connect. In fact, we recommend direct connect as the mechanism to communicate back to the region because it will give you the most predictable latency and bandwidth, given that it's being carried over our backbone network. Through this VPN tunnel, we were able to send management traffic from the Outpost proxies to the Outpost edge device, and then that edge device will replay the management traffic into the internal network of the rack. And ultimately, from the server's perspectives that are in the rack, they're receiving control plane traffic from our control plane in the region as if they were sitting in the region. They can't actually tell that they are not in the region. Likewise, the Outpost proxies represent the outpost within the region, and the control planes talk to the Outpost proxies as if they were servers in the region. So the kind of trick behind Outposts is that we're tricking both the Nitro servers and our control plane into thinking that they're both sitting in the same place, when in reality they're not. They're connected over potentially a large distance. The key thing that makes Outposts unique and special is that because we are connecting these things together over a long distance, we're able to use the same control plane, the same hardware, and the same software under the covers. And importantly, that means it gives you the same experience with AWS. If you are developing high-level applications, whether it's a Node.js application or even a containers-based application, you're typically going to pick a couple instance types, and you're going to test your application on those instance types. Now, it's very unlikely that your Node.js application isn't going to functionally work on a C5 4x large if it works on a C5 2x large. However, when you do performance testing, you might find that you actually need a certain ratio of cores to memory, or your application doesn't scale well past a certain number of cores, or there's a million different things that make it difficult to have the same performance on different pieces of hardware. One of the things that was critically important to us with Outposts is that we wanted to make sure that if a customer developed an application and they tested that application on a C5 2x large, that when they used a C5 2x large within the context of an Outpost, it behaved exactly the same way. It has the same scaling characteristics, the same networking performance, that you as a user don't have to think about porting your application to the Outpost, that it just works. And that's what we achieved by utilizing all of the same mechanisms. I've talked a bit about networking so far, and networking is one of the areas where we had to introduce new concepts in Outposts. First, to launch an instance into an Outpost, the mechanism that I use is actually launching to a specific subnet. So when I create a subnet today, there's a number of things that I can select. I can select the availability zone that the subnet's in. I can select whether I want dedicated tenancy or not. And as of Tuesday, when we launched Outposts publicly, you can now select an Outpost ID to associate the subnet with. And when you do that, all launches to that subnet will appear within the Outpost. Now, you can have multiple subnets. You can have as many as you want within that Outpost. You can also use multiple accounts, as long as those accounts have access to the Outpost ARN. And you can share the Outpost ARN with any account that's in your AWS organization. One of the interesting features that comes from this subnet-based launch model, though, is that you can actually have VPCs that span both public capacity and your local outpost. So you can write applications that seamlessly work across both the public region and your local capacity without having to do anything special in terms of network connectivity. You can just use private IP addresses within your VPC. Because we're just using standard VPC mechanisms, you can still use internet gateways, transit gateways, and VPN gateways, And in the case of an internet gateway, that will actually egress traffic through the region. So in order to egress traffic and ingress traffic from the local network, we've introduced this new concept of a local gateway. You add a local gateway into your route table, just like you'd add any other gateway, and you can choose to send default route, or you can send a specific CIDR block to the local gateway, and that controls which traffic in your VPC is going to enter into your network. Traffic that goes through the local gateway, there's no additional charge for because it is on your network, and it is literally one switch hop away from wherever you want to put it on your network. So by sending traffic through the local gateway, you can actually achieve very, very low latency. In our own testing and configurations, you can get well under 100 microsecond latency to something sitting next to an outpost. So if you have an application that needs really, really low levels of latency to AWS capacity, you can choose very specifically where in your network and have really deep control over what that latency is going to look like. In addition to new networking concepts like the local gateway, ordering is obviously going to be a little bit different with Outposts. Now, before I talk about the ordering process, I'll mention that from a pricing perspective, an Outpost comes as a 3-year reserved instance. And the pricing model works exactly like 3-year reserved instances work. You can do partial upfront, all of the typical reserved instances pricing constructs. And that pricing includes everything about the Outpost. It includes the installation, any servicing or hardware replacement. You're really paying for instances just like you pay for instances in the public region. Now, before we can actually bring the Outpost to you, we have to collect information from you about what the site is that the Outpost is going to be installed in. This includes the actual street address, what the power requirements are. So we want to understand whether you have 5, 10, 15 kVA positions so that we can help show you which outposts will actually work for your configuration. From a power point of view, we support single-phase or triple-phase power drops, and we support a range of industry standard plugs. We also need to know more about your network. One of the things that's particularly important is understanding the types of optics that you use and what types of network, what the uplinks are going to look like from a bandwidth point of view. If you've worked with 100 gig networking in the past, you'll know that compatibility among switches and optics is pretty complicated. So we're trying to collect all that information ahead of time so that when we do the installation, everything goes smoothly and we can bring everything that we need to make it work. And then finally, weight restrictions. Because we are delivering a fully installed rack that weighs somewhere between 1,000 and 2,000 pounds, we just need to make sure that we can get from the loading dock to the final location, and everything's going to go smoothly without damaging any of the floor. Generally speaking, we can work with you on making sure the install happens properly. We just want to make sure that we know all of the information we need ahead of time. After you've helped tell us about the location the Outpost is going to be installed to, we can then show you a set of Outpost configurations that are compatible with the site that you've chosen. An Outpost configuration consists of a variety of compute, so that comes in the forms of EC2 instances, and EBS storage. And so you'll see configurations that have, as an example, 11 terabytes of EBS storage, and then a collection of C5, M5, and R5 instance types. And you can choose what the right balance is for you, what the right mix is for you. As part of this week's launch, we have configurations that support C5, M5, R5, I3EN, and G4DN. And the C, M, and R instance types also can come with disk, local instance storage. You should expect that over the next year, every Nitro instance type that we support in public regions will be available in Outposts, including things like the M6G Graviton 2-based platforms that we just recently announced when they come out of preview. Because it's the same hardware, it's pretty straightforward for us to include it within the context of an Outpost. And finally, if you look at this set of configurations in an Outpost and you don't see one that fits your exact needs, we're very happy to create new configurations. We started with a fixed catalog just because we wanted to try to simplify the ordering experience, but we're very, very happy to help work with you on custom configurations. Finally, after choosing a configuration, you submit an order. And when you submit an order, the next step will be an installation team reaching out and scheduling an installation appointment. Installing an Outpost is not quite the same thing as ordering something from our friends in retail. We don't want it to just show up on your doorstep one day and you have to deal with it. So we do want to have the conversation about what the best time is to do an installation, make sure everybody's going to be there, and ensure that it's a very successful event. So for the actual installation day, and I'll say that I've done a pretty good number of Outpost installs at this point in time. You might actually even see me at your installation, as I really like doing these installs. A team of Outpost technicians will meet you or a representative from your organization at the loading dock. We actually uncrate the rack. We do everything in terms of actually installing the rack within your data center. We'll roll the rack into position after we've inspected the path to the rack. We need you to provide an electrician to energize the rack. This is just because of local code requirements. And then we'll connect the uplinks into your network. We'll perform some final rack configurations. And then shortly after we've done some basic testing to make sure that nothing bad has happened in shipping, we'll turn over the rack and you can begin launching instances and creating EBS volumes. One of the things that's been really fun about doing these installations is that I've talked to a lot of customers that try to stand up racks running private cloud software in their data centers. And some customers have told me that it typically takes them 6 weeks to do an installation because they have to actually assemble the rack, they have to install all the software, they have to work with the networking team to figure out what it's going to look like. And this is surprisingly common. It can take a really long time to install a full rack in a data center. Our installs, as long as everything goes well, the position has been set up the way it was supposed to be set up, they typically take 4 hours. And this is actually longer than it takes us in our data centers, and that's just because our data centers are really, really optimized for this. But the really cool thing about an Outpost is you can get started right away. There's no long waiting. It's something that can be installed very, very quickly, and you can almost instantly begin using it. Werner likes to say that all things fail, and he's absolutely right. We put a lot of work into hardware quality. We have a lot of data on hardware. We know our hardware is among the best in the industry in terms of reliability, but ultimately it's going to fail. This is just the nature of physics. And to deal with that, we've made sure that all of the active components in the rack are redundant. There are multiple switches, multiple power supplies, and as long as you're building a well-architected application, for instance, you're using auto-scaling groups to relaunch instances when they fail, then there's no single component in the rack that can fail that should cause problems for your application that aren't recoverable almost instantly. And as part of an Outpost, we actually reserve a set of instances within the rack to make sure that as things fail at the rate we expect them to, you always can stop, start, and there's capacity available. If you want to manage the availability of your application yourself, you can override this and actually use that extra capacity, but we highly recommend that you let us manage that because we just have more information about what the right amount of buffer capacity is. Once we've detected that there's a failure, we'll begin shipping out a component to replace that, and we'll contact you to schedule an appointment to do the replacement. Our goal to meet our availability requirements is a 2 business day replacement. So it's not something that you're going to have to page people into in the middle of the night. It's something that you can do hopefully in a normal process for your data center. And I just want to stress that this all is built into the cost of an Outpost. You don't have to pay when we replace hardware. You're just paying for instances, and we're responsible for making sure those instances always keep working. Now, we've talked a lot, we've done a lot of slides. I have to go back to showing pictures of hardware because it's the end of reInvent, and this is really what I love talking about. So one of the cool features that we can show now that we're doing Outposts, now that you can touch the actual hardware, is something we call the Nitro security key. Werner showed in his slides that part of the Nitro system was to ensure that all data is encrypted at rest. And this is really important because there's actually a big challenge in managing data centers that you may or may not have dealt with before, and that's what do you do with hard drives? If you're managing a data center of general purpose hardware, you're not always going to be sure that all of the data on the hard drives are encrypted, and even if they are encrypted, how those keys are managed. And so a lot of data centers have very strict policies that no persistent media can leave the data center without being physically destroyed. Now, this creates a lot of logistical problems. One, the physical destruction of hardware produces waste. Waste isn't good. Tracking that hardware to make sure that it's all being destroyed can be complicated and is kind of a logistics challenge. And so with the Nitro security key, we take a different approach. Because we've designed the system to be that everything is encrypted by default, we can extend that encryption to an external device, and so that the key that's used to encrypt the data is re-encrypted from this external device. And it's much, much easier to physically destroy this external device to ensure that all of the data has been destroyed. Physical destruction, it turns out, is important because even if your software destroys all of the data when you terminate an instance or when something fails, you have to anticipate every possible hardware failure scenario, including things like capacitors blowing out on the motherboard, causing it not to power up, networking adapters failing, making it impossible for the control plane to reach. You need some way of physically destroying data, otherwise you can't be sure that the data is destroyed. And this is how we do it. So this is a device that's about yay big. It fits on the top of the server, or the front of the server, and it actually fits over the latches for the server such that you can't remove a server from the rack without first removing this device. And you can see on the side there's actually a bullseye, and that bullseye is for a screwdriver. You can use a hand screwdriver or you can use a power drill. And this screw sits on top of a microcontroller. And that microcontroller is a very simple microcontroller that stores a tamper-resistant key. And when you crush that key, what you're doing is you're physically destroying one of the keys that's used to encrypt the rest of the server, and therefore you're physically destroying all of the data within the server. This means we have a very simple mechanism for you as the customer to know that all of your data has been destroyed before we actually replace the node. And this is just one of the types of innovations that we do in hardware, but it's now one that because Outposts can be in your on-premises environment, you can actually see and understand how we do it. I want to talk a little bit about how we're thinking about services on Outposts. We announced a number of services as part of the GA launch, and I wanted to use this to talk a little bit more about how we're thinking about services. The first observation is we couldn't just take our entire service catalog and lift and shift it into an Outpost. We could do that. It's just EC2 capacity. It would functionally work. But it would not deliver on the promise of Outposts. We'd have the same problem that we had at the very beginning of the presentation, where all of a sudden the entire rack was being utilized for all of those control plane services, or we'd be replacing that with monolithic software that doesn't actually behave the way that the services in the region are. So the goal for Outposts with services is any service that we bring, we want to be very frugal about the capacity we use. We only want to bring the things that we absolutely have to bring. And we don't want to create an uncanny valley. It has to be the same service that we use in the public region. ECS, the Elastic Container Service, is a great example of an AWS service that just works on Outposts and has the right behavior out of the box. So with the ECS service, you launch a number of instances. In this case, you would launch those instances into an Outpost subnet. And those instances run an agent that talks back to the ECS control plane. Because they've already split the launching of the data plane instances from talking to the control plane instances, it's very easy to have the control plane reside back in the public region while all of your data plane nodes run locally. The EKS service is a service where we did have to teach it how to work with an Outpost. We had to do a fair bit of work, although not a tremendous amount. in order to create that split between the worker nodes and the control plane service. What makes EKS different from ECS is that instead of having one control plane that everything utilizes, there's a Kubernetes control plane per cluster in the public region. So we had to teach the EKS control plane how to launch the control plane cluster separately from the way that we launch worker nodes. In addition to AWS services, as you think about building your applications for an outpost, one option is lift and shift. You can absolutely lift and shift your application to run in an outpost. But I think the more exciting architecture to explore is how do I tease apart the aspects of my application that really need to run locally from the things that need to run remotely. As an example, if you have a database-based application, maybe a traditional three-tiered architecture, you might need to have your database run locally because you have a bunch of on-premise things that are communicating with it and need low latency. But it's really common to have some kind of batch job, something that maybe runs late at night and is doing some kind of HR report or some kind of business logic report where the latency isn't as important. And the best thing to do would actually be to utilize spot instances where you can get elastic capacity in the cloud and do batch type workloads. And so I think those are the architectures that over the next couple of years, I think you'll see a lot of exploration of. I think that's where you get the real value of something like Outposts. These are the services today that we have optimized to run locally within an Outpost. All services are accessible via an Outpost, but these are the ones where we've really teased apart the data plane and the control plane. And that's EC2, VPC, EBS, ECS, EKS, EMR, and RDS is currently in preview. Now for RDS, that is not Aurora. That is the other database types because Aurora is fundamentally a 3AZ architecture, so we're still working on how to do that split. But the other RDS databases are available in the single AZ variety, and that's in preview today. The other thing we pre-announced is that we are building a version, or we are modifying S3 to also support Outposts. Now, S3 is obviously difficult for Outposts because of the fact that it is fundamentally a 3AZ architecture. However, it's also something where customers have been telling us that it's really important to have the ability to have local buckets. And so we've been working with the S3 team for quite some time now to build an architecture where we can preserve all of the same characteristics of sameness, but still offer customers the ability to have local buckets. All right. So that was the end of the talk. I have a little bit of time for questions. If anybody wants to ask a question, if you can just come up over here and we can do questions.